Swayam Prabha. Digital India. Educated India.
Hello and welcome to the week 4 of medical image analysis course. In this week, we'll talk about non-rigid registration techniques. Specifically, we're going to look at two algorithms, very highly cited and popular algorithms for non-rigid image registration. And there are several free implementations of these available. We will talk about them in the following week, that is week 5. So in many applications, the transformations that we use for registering two images from the same patient even, they cannot be approximated by rigid transformations or not even affine transformations. This is because the anatomies might deform and between imaging sessions, and that might also be because of the patient's pose. So for instance, in some applications, the patient lies in the bed for a prolonged period of time and images are acquired over a particular anatomical location. But even in that situation, because of respiratory motion, there could be some deformations which cannot be approximated by rigid body transformations, right? And there are other applications wherein the patient is followed over a longer period of time. He has multiple imaging sessions, and even those sessions he or she might not adopt the same pose. There is of course going to be deformation of our various organs. So if rigidity cannot be assumed, then the most general non-rigid registration transformation is basically the estimation of a deformation field or a displacement field. So this is nothing but the estimation of a displacement, which is a vector, because you need to have components in x, y, and z directions. A small displacement for every pixel in the image, or in some cases a control points. There is a bunch of pixels which you choose as control points. You estimate at least the displacement for those pixels. Okay. The problem with this approach is that if you consider any grid, let's say even a 2D grid, and if you're trying to estimate a displacement vector for every pixel in that grid, if every pixel can move in almost any direction, right? So there is no constraint there. And so that means that the problem becomes that much harder to do. So then to limit the search space, to make it doable, then you typically have a constraint or a regularization that is imposed on the deformation field or the displacement field. Okay. So a lot of the algorithms differ on how the displacement fields are regularized, and in some cases even how the displacement fields are estimated. So we are actually going to look at two different algorithms which estimate the deformation field slightly differently. Okay, so this is where this is the general approach to non-rigid registration. So there has to be an estimation step of the deformation fields, and followed by a regularization over the estimated fields, because then so that you can actually limit the search space. So once again, when in many problems the loss function is regularized so as to obtain a displacement field which is already smooth and constrained and all that. In some cases, because the algorithm itself, the way it's done is that once you estimate the displacement fields, you can regularize them. So we're going to look at two different methods which do that, which what I just described in this week. But just to reiterate, this is evidently a very difficult problem, and there are lots of issues here still. And in general, you would do non-rigid registration following a rigid registration, right? So you would actually do rigid registration to bring two images close enough, and then you would do the non-rigid registration following that, so that these displacement fields that you estimate as part of the non-rigid registration algorithm They basically the displacement fields are the transformation vectors, right? And they can only be very small, so you can't. So if you do very large deformations per pixel, you would end up doing something unphysical, and for instance, breaking the image into two, etc. Those are not allowed transformations. So typically, these displacement field estimates, they only work for very small displacements. Small in comparison to the organ of interest, and in general, what could be feasible displacements that problem allows. So in the next few videos, we will look at two different algorithms. We'll talk about how to estimate them. So in these two papers, typically there is also usually a moving image and a fixed image. The notations might differ slightly, but typically they are either denoted by A or B. For instance, something like this, A comma B. I think I used a very large thing. So it's either A, B, or in some cases F and G. Okay. F and G is more commonly used, I think, but anyway, so these are pairs of images. One you would consider as the moving image, typically G, and the other one you would consider as the fixed image, and all of them can be treated as either 2D or 3D images. In fact, both techniques we are going to see work on 3D images as well. We will look at the results and demos of these algorithms the next week. So this is where I promised week 5 is where we look at some of these case studies. So we'll look at these case studies where we'll get this demo. I'll try to provide you some freeware that is available to actually try out these algorithms. Okay. So we will now look at the Therians Demons algorithms and the freeform deformations algorithms in the next couple of videos. Thank you.